And put your slide. Listen, you can just start the display. Slide.
It's visible?
Yeah, you can go to that presenting mode. Slide show mode.
Okay.
Okay, fine. Just wait for do the introduction.
What, sir?
Wait for 2 seconds. PDF will do the formal introduction. Then we can. Okay, Chiranga.
Shall I start, sir?
No, just 1 minute.
Hello?
1 minute. So,
Okay.
previous will give an introduction to you and then we can start.
Okay, sir.
In Chennai, we are having and
Shall I start, sir?
okay, we'll start.
Okay, thank you, sir. Dear participants, good evening. CSI Chennai, ACM Chennai, IEEE CS Madras cordially invite you to a webinar on deep learning algorithms for cloud robotics by Dr. Chiranjeevi Karri, C4 Cloud Computing Competence Center, University of Beira Interior, Portugal. Cloud robotics is an emerging field of robotics rooted in cloud computing, cloud storage, and other internet technologies centered around the benefits of converged infrastructure and shared services. In this webinar, Dr. Chiranjeevi will give an overview of security algorithms like cryptography, image processing, and fully homomorphic encryption schemes. He will also highlight some experiments that conducted for face recognition through various deep learning algorithms after encrypting the images in oral database and experimental results showing improvement in speed and accuracy of recognition. Dr. Chiranjeevi is a postdoctoral researcher at Cloud Computing Competence Center Lab, University of Beira Interior, Portugal, under grant sponsored by European Union 2020. He received BTech in 2003 from JNTU Hyderabad, Andhra Pradesh, India, MTech in 2003 from JNTU Kakinada, Andhra Pradesh, India, both with the highest honors, and PhD in Veer Surendra Shaw University of Orissa, India. Since 2010, he has been with GMR Institute of Technology, India, where he is an associate professor. His research interest includes cloud robotics, security, deep learning, and image processing. He is having experience in teaching more than 16 years and also published many papers in national and international journals and conferences. Over to Dr. Chiranjeevi. Thank you.
Thank you. Thanks for your brief introduction. So here is my presentation, deep learning algorithms for cloud robotics. It's my around 1 year, 2 months of experience I'm going to share with you. So if any queries or if anything else you want, let me know at the end of my presentation. And before starting, I would like to thank you all to attend this presentation. So here is my content. First, I would like to know about what's the difference between the machine and robot and why we moved on to the cloud robotics. In that, a special problem that is robot face recognition, and a part is object detection too. And with some algorithms like PC and deep learning algorithms, various deep learning algorithms. And as we are using cloud technology here, so there may be a chance of insecurity of data. Those problems are deal with this cryptography, image processing based algorithms, and finally fully homomorphic encryption. So this is the evolution of a robot as like a human being from those forest days to everything you are seeing now in a mobile. That's the evolution here. In same way, this cloud robot is also replaced from these days. We are replacing the human beings with the robots for several tasks. And so what's the difference between a machine and a robot? So machine means it's without any intelligence, whereas robot means it has some intelligence. So that a robot can think, can do the tasks in better way. Whereas machine means it's simply without any knowledge, without any learning process, they do the things. Whereas robot do the things by learning, by adapting their self. It's almost like how a human being adapt to the technologies like that. And there are various kinds of robots we categorize usually. That's like service robots. So a simple example is a vacuum cleaner and mower robots, and same way domestic robots and some security robots. Mostly we see it in industries, and same way robots in hospitals. These days, operations are done through robots also. That is also possible. And robots in agricultural industry. This is also very interesting topic these days. And robots in medicine, in finding a cancer detection, and so many diseases. One can use robots. In some similarly, robots in surgery also, and some robots to play. That is toy robots also there for fun for kids. And it started in 1495 about the robots, and various people are using these robots. Like this is the cheetah robot. It looks like it behaves like a cheetah. Tiger, called as a cheetah robot. It looks like a tiger. So how fast the tiger is? In same way, this is also very faster. And same way, robots are used in space for several applications. And this is the cloud robot. Imagine people are using this. And same way, Google self-driving car. And then this is a Sophia robot, which speaks like which acts like a human beings, which do things like a human being, and which responds to the people as like a human beings. It's a and this is the first robot given a citizenship, that is a software robot. Then we moved on to the next technology, that is cloud technology. So cloud technology replaced with so many things, like you can connect whatever the things like server, network, mobile, desktop, laptop to the cloud technology. It's the use of this cloud technology is to simplify your things, and which reduce the size, cost, and so on. And in robotics, the main challenges here is speed limitations in robot. So suppose if you see it in a robot in a crowded environment where the robot will see the people and to do some tasks. So their speed is very important. So we have to see we have to look onto this speed limitation issues, and same way onboard circuit limitations. So robot can't carry much things. If it is carries much things means power requirement is also more. So that is one issue. And same way, so limited processor and memory limitations are also the one challenging task. Not only these things, many more are there. And the answer to all this is cloud robotics. Cloud robotics. So in cloud robotics, we adapt the robot technology to cloud. And one more thing here is in cloud robotics, not only adapting the cloud technology, in similarly, robots itself share their knowledge like this. They share their information, and with that sharing information, they learn the things better and better, so that you do the tasks better and better. So that is also one possibility. And cloud robotics, the main idea from cloud robotics is a mission to mission interface, or mission to mission communication. So here you can see the several robots share their information themselves and with the cloud also, so that they learn the things, they understood the environment very well, so that they do the tasks in better way. So the origin for this cloud robotics is mission to mission and mission to computer. And this is one example of the cloud robotics. This is seen from Matrix movie released in 2003. So wherein this is assumed this as a robot. So after this scene, she has to move with this helicopter, but she don't know how to drive this helicopter and all. Now she will call to another person. You can assume this is a cloud. He will program. He will program the required things and given to the robot, so that it can fly from their place to another place with that helicopter. So that's the advantage with cloud robotics. So whenever the robot needs something, it can easily ask to do that. That's the advantage of cloud robotics. And there are various cloud robotics so far exist, and it was first coined by James Kuffner in 2010. This one is developed, and after invention of cloud technology and the Internet of Things, the James Kuffner coined this. And in that there are several categories like autonomous mobile robots. The best example for this is Google self-driving car, and cloud medical robots also are there, which helps for the doctors to better diagnose the diseases, and assistive robots to help older people, and also and industrial robots for it integrates the customers and the business partners in integrated robots. And Robo Act, it is a European Union funded project, a very big project, and it is supported by Raiput and NOROP. So this is a one cloud robot technology. It's under process of implementation, and same way, some robot operating systems are also available to buy. So, and similarly, C2 Arvo Cloud Robotics is also there. And RoboBrain is still, some people are implementing this RoboBrain also. So, brain means it's a replacement of human brain, more or less. So, here I want to show you one video about how Imagine people are using cloud robotics for their services like
Sir, is there any audio for that video? We can't hear the audio part of it.
yes, it's not requirement, it's not so mandatory.
Okay.
Just visualization is important here. That's clear? Visualization is okay?
Yeah,
Yes.
yeah, it's fine.
Thanks for watching. So, as you saw here, how Amazon people took the advantage of this cloud robotics for their services like packing the goods and delivering the goods and arranging them in proper way. That's the advantage with one advantage with cloud robotics, and one more miracle is with Google self-driving car. So a car, they implemented a one car without a driver. This is also possible with the cloud technology, cloud robotics. In addition to this cloud technology, they adopt the sensors technology also for detection of objects and any abstractions and all. So this is a Google self-driving car. And some cloud providers includes Google Data Center, Amazon Web Services, Microsoft Azure, and almost all MNC companies are maintaining their own cloud. And the same way, they are distributing their cloud to people also. You can see here, this is the Amazon people, how they are using, how they are giving us cloud to the various users. So you can see here. So this is the Amazon people are giving AWS services here. So you can log on to the, you can create your account here. And once if you log into this for a period of 1 year, it's for free. And you can have it's like simply you can have one computer with various operating systems with memory sizes. So whatever you want to require, you can go for that. So in that way, say these are the products and solutions, pricing. So all things are given. And same way, this Google people are also providing this cloud services to the users. It's like it's as like buying a internet like that. So that's the advantage with this. And same way. So here I am living here. There also one cloud center is there. So this is the cloud center where I am living now. So here is the pic of it with my colleagues. But while using cloud robotics, the challenges here is cloud may be a private. If it is private, there is no question of security. But whereas public and hybrid clouds, as this is public, so many users may use this cloud. So there may be a chance of insecurity here, and those issues are resolved with cryptography algorithms, image processing based algorithms as of now. But later on days, like after 2009, we moved on to the fully homomorphic encryption. So it's a very advanced technology. So people who want to do some research on security, especially, I refer this fully homomorphic encryption. So the advantage with this fully homomorphic encryption is that, so there is no question of decryption here. There is no question of decryption. So all arithmetic operations or logical operations, whatever the mathematical expressions you want to do, you can do it in fully homomorphic encryption. That means all operations are performed on encrypted data only. That's the advantage with this. And same way, you can decrypt by means of a private key. So in this, especially I deal with one problem, that is robot vision. That's through recognizing the faces, human faces. So the application here is in military applications. So whether the enemy belongs to friendly person or a enemy, to that I deal with this problem, that is face recognition. So face recognition means it's like recognizing the unknown faces by means of some data, some collection of data. So in same way, object detection also is possible with this cloud technology. It's mostly used in self-driving cars. And face recognition, the major thing required for face recognition is we need to collect some data. This is the data, and we have several various data sets available in the literature. And some people are working on a collection of data also. So, and they are publishing a good paper, publishing good papers also. So once a data set is generated, it's thousands of images of different persons with different positions and different expressions like that. And these will be trained with some training algorithm. And based on this training, that algorithm can know a unknown face by doing some operation on a input image. That is called as a face recognition. So in similar way, another task is here is in face recognition. The image may be a blurry one, or maybe a sharper one, or maybe have some noise also. We have to look after all those things also by doing some pre-processing stage. And also, in some cases, there may be so many people in one image with the different poses like this. So anyway, for initially, the algorithm will do where the faces exist in an image. Thereafter, it proceed for the process. Whereas in face recognition cloud environment in encrypted domain, so what I do is whatever the database is there, that is encrypted with some encryption algorithm, maybe a cryptography or image processing or fully homomorphic. And this encrypted versions are keep into the cloud server. Suppose I assume that this is a robot, want to know who is this person is. Okay, then this robot encrypt the input image with the same algorithm what we used here, and then we sent it to the cloud server. Now in the cloud server, the all algorithm will runs, and to know whether this person exists in the database or not. If it is so, then it will send back who is that with some label, or sometimes it's a yes or no, or with sometimes with some label like that. So here the robot, what it need is only to take a picture of the person, and some encryption algorithm is enough. But rest of the things are done by cloud server, so that the challenges like memory requirements or onboard circuit limitations, and same way as the cloud servers processors are very high speed, so that high speed limitations are also avoided with this cloud robotics. So this is a simple face recognition to principal component analysis. Whatever the data set is there, that is encrypted with some encryption algorithm, whatever it may be. That encrypted faces are in the database now, and our algorithms are trained on the encrypted data. So whenever an input image comes with, then this input is compared with all the database, and if its threshold is some above value, then it will say yes, this is the person. If its value is less than threshold, the person is not in the database. Some people are working on this random number generator, and some people are working on continuous learning. By suppose this person is not in the database, then automatically it will add to the database here. That is called as a continuous learning. Some people are working on that also. So here what we do is, I want to explain this with some example. Suppose this is the database. Let's assume that these are, you can assume an image has a matrix of size 100 by 100, and initially that will be converted into vectors. So a vector becomes like this, vector 10,000 by 1, and now we have to calculate average of that and subtract it. That we call as a face vector space A. And like that, if it is a 40 database, then it will comes to 10,000 over 40. Then you have to calculate the eigenvectors by doing this simple operation. But it leads to a size of this much size. It's very huge. So that's why we go for a dimensional reduction technique, where this A transpose is reversed here, so that size becomes 40 by 40. So that is called as a eigenfaces. That means this whole database is represented with a small things like this. Okay, so you can get by this one by means of some eigenweights here, eigenweights here. So whenever a new image comes, based on we can extract the eigenweights of that, and which weight is similar. That is the unknown phase. Now let's move on to some image encryption algorithms. This is first one is a pseudo random generator, where two keys are generated with logistic map and linear feedback shift register. In logistic map is one where it generates so many elements or a matrix of different sizes, and the beauty of this is none of these values are similar. That's the beauty of logistic map. And another key is generated with a linear feedback shift register. Suppose initially this is the number, then after some iterations it will generate by doing this it will generate some key. Those keys are given to once again given to a XOR operation to get a one key, and that key, with this key image is encrypted, so that we will have a encrypted image here. So this is the one procedure of encrypting the image. And now this is a cryptography based encryption algorithm, that is Hill cipher. Previously these are used for one-dimensionals, but these days we have moved on to the two-dimensional like images, and sometimes you can use it for videos also. And it was invented in 1929. The basic idea here is just identifying by replacing A values with corresponding numbers like 0, 1, 2, 3 like that. Okay, so multiplying each block by K and then reduce mod 26. And similarly, decryption is opposite version of encryption. Suppose I want to encrypt this symbol LOVE. So as a partition that into two parts with the key, secret key is this, then L corresponds to 11 and O corresponds to 14. So we replace that with 11, 14 here, and same way VE with 21, 4, and multiplication and mod 20 after mod 26. We can have this, and its equivalent characters are CDQF. So this is the encrypted version of our LOVE, and we can get back the original one by doing some reverse operation, by doing some multiplications like this until this value becomes equal to 1. Here 1. So that is 1. So once you did this, then you have to do the inverse operation like this, AD minus BC inverse. So 17 inverse is like mod 26 by 23. That's why it's a 23. And similarly, minus 3 is 23 and 15 is 11. So after doing mod 26, you can get back the with the this is a private key. After doing this multiplication, doing mod 26, we can get back the original one LOVE like that. So that is a Hill cipher. And another encryption algorithm is RSA algorithm. It was invented in 1978. It is also called as a partially homomorphic encryption. I will discuss about that later on. But in RSA, we have to choose two PQ values. From that, we get n value. Then our phi of n value will be calculated, and by choosing d values, suppose let's assume that d value is this and e value is 23. Then now let's move. Let us assume. Let us choose the first pair of encryption, and e is equal to 23. I chosen these values. E is equal to 23, and d is equal to 2087. Then I want to encode this. To do that, I partition that into 3 digits of each. And in encryption case, this is my one key and this is another key. Then it becomes like this. In reverse process, this is my private key, and this one is a public key. Everybody knows this, but this private key, I only know that. So if I have this, I can get back my original one like this. So, but thing is, in encryption algorithms, the main important thing is how much is the security, and what is the key size is also very important, and this must be inversely proportional. With less key size, we should have a high security. That comes with the advanced encryption standard AES, where it was invented by NIST in 2001, and its key size depends upon number of rounds you do. Like if you do 10 times, 12 times, or 14 times, its corresponding key sizes are here like this. It depends upon number of rounds. So you can see here, these are the different keys that feed it to the here to rounds. Then finally, you will have some encrypted ciphertext here. As the number of rounds are more and more, key size is also more. As key size is more means it is difficult to get back the original one. And this is another kind of image encryption algorithm, that is image processing based. That is DNA. In DNA, it's developed based on the DNA of a human being, like A, T, G, C, and its corresponding values are represented here. Based on this table, you can choose any of these tables. So that is what kind of table you took for encryption. That is one key, and same way how we are representing A, T, G, C values is also another key here. So here 1 is replaced with T, so 1 is with T, and 10 is C, like that. So and so on. And this is the paper which given this DNA encoding. And similarly, another one is a genetic algorithm. It's I think everybody knows about it. It's developed based on the genetic procedure of human beings, wherein there are two processes, crossover and mutation. The crossover is just simply replacing this with this and this with that. And similarly, mutation means only either of any of the bit is replaced with ones with 0, and complement just simply application of complement like this. So here the key is how many bits you choose for crossover, and similarly which position you mutate. That is also very important. That's the keys here. And another one is image processing based. That is bit slice. Bit slicing means just whatever the image is represented with its equivalent binary numbers, and all LSB comes with first bit slice, and the last MSBs comes with 8-bit slice, and first bit plane is rotated by 90 degrees, 180, 270, like that, and its equivalent encrypted matrix is this one. And similarly, in case of decryption process, if you do 90 degrees, do it in 270, and like that. So here, the key is whether you do with 90 degrees or 180 or 270, that is the one key here. And whether you took a first bit slice as a MSB or LSB is also one more key, that is called as a bit slice. And another one is RCP, rubric cube principle. It's this is depends on rubric cube, as we know all. So in rubric cube, we rotate in right direction or left direction by 1 or by 2, depends on that. It based on here the key is how many times we repeat, we do the circular shift or right circular shift or left circular shift, or how many times we did that. That's the key in rubric cube principle. And here I want to show you some results so far discussed encryption algorithms and with the principal component analysis. So this is the original image from overall database, and its histogram is this one, and horizontal and vertical scatter plots are this. The scatter plot shows us the relation between one pixel to next neighboring pixel, one to one. This one. So after encryption algorithms, various encryption algorithms, these are the after encryption, these are the algorithms and its respective histograms and the horizontal vertical plots here. Horizontal vertical scatter plots are here. Okay. So if you look at here, this is the input image, and its histogram is has two hills like this. This one is one hill, and this is another hill. So a better histogram, a better algorithm, one can say based on the histogram also. So if you see here, this histogram is uniform. This histogram is also uniform, and these are with DNA and hill cipher. Whereas in GA, you can see whatever the inside of this. So one can know what inside is. The means its security is less. Whereas in RCP and RSC also, you can't see what's inside in this image. So security is more intense. And these are the some overall database images. And I measured the security in terms of NPCR, USCA, PSNR, and correlation coefficient, so on. In that, if you observe here, GA in terms of security is less, GA, as compared to others. And similarly, these are the time to encrypt one image. Among these, AES takes a lot of time, and CHOCOS takes very less time. And here the results of recognition accuracy with various encryption algorithms here. If you look at here, this no encryption 80.4 and GA encryption is 80.4, more or less are same. But as you saw before, the GA security is less. So there is a compromising between the security and the recognition accuracy. There is a trade-off between that. And similarly, I did some number of people, training people are more. So as it goes down, number of training people, then recognition accuracy is also getting down here like that. And finally, my motto is to do the experiment on robot as well as in cloud. These are the specifications of cloud, and this is the specifications of robot. Obviously, cloud is very RAM size is 40 GB and robot is 32 GB only. So I assumed robot as my desktop here. My desktop is this, and this is the cloud server. And these cloud servers are provided by UBI. And if you see here, I almost time to recognize a face single phase is off with the cloud. That's the improvement in with the cloud. The speed of recognition is very fast. It's almost all half of the robot recognition time. Then I moved on to the instead of PCA, I want to use deep learning algorithms. So in those deep learning algorithms, you have to know about artificial neural networks. It's developed based on the human brain. So human brain functioning like this. So it has some inputs and some weights, and the multiplication of these versions are summed together, and it should given to some activation function. This activation function may be there are some kinds of activation functions are there. Mostly used one is sigmoid function. So based on this sigmoid function, it gives us some outcome OJ. So depends upon the input. As the input is variable, its outcome is also variable. So based on your applications, you can train the ANN by changing these weights. So here you can see I am training this ANN with to recognize the digits from 0 to 9. That may be this that image may be of a different shape. Some write like this 2, or somewhere write in another fashion, or in some vertical like that. Even though whatever it may be the case, it should recognize my ANN should recognize. If I give 2, it will recognize 2. In same way, here AN is trained for recognize a dog or a cat. A dog of different kinds. As we know, we have several kinds of dogs and cats also. So my ANN is trained to recognize whether the given one is a dog or a cat. Like this. So this is done by adjusting these weights, simply by adjusting these weights. That is called as a training process. Whereas in testing process, how many inputs are given and what's its accuracy depends on that. I can say what's the accuracy is. And with the ANN, some drawbacks are there. That's why we moved on to the convolutional neural networks. It's mostly this technology is adapted from segmentation. Where in segmentation, what we do is we move one channel kernels all over the images like this. This is RGB image. So I have RGB and its corresponding kernels are here. Then after multiplication of each element with its corresponding kernel and sum together, we can have its elements like this. This is first element, third, fourth, like this. Summation of all these elements is like that. And after convolution, then I should go for the decision, and then pooling is applied. This pooling is to reduce the size here. So here this is a 4x4 image becomes 2x2. In order to reduce the size, we go for a pooling. This pooling may be a max pooling or average pooling. In max pooling, about 2 or 4 elements, we take a maximum of this 8, 6 like that. Whereas in case of average pooling, we do the average of it. And then such kind of this kind of things maybe this combination can be repeated for better future extractions like this, like that. And finally, we will apply for a classification to classify whether the input comes under a car or truck or van or like that. So this is called as a deep learning algorithm. I want to clarify you what's the difference between a machine learning and deep learning is. Machine learning means only up to this point. This part is machine learning. That means machine learning only extract the features only, and those extracted features are classified with some other classification algorithms here, like SVM or whatever it may be. But whereas in deep learning algorithms, that comes with both, like feature extraction and classification also. That's the difference. And these are very standard and flexible for all applications. Some kind of deep learning algorithms. That is, first one is LeNet, and it was implemented in 1995, and it's used for low resolutions black and white object recognition. Here, this 5 indicates that there are 5 layers here, 5 layers here, excluding the pooling layers. 1, 2, 3, 4, 5. That's why it is called as a LeNet 5. So here, after 5 by 1 relation, you can see the different values here. This all depends upon the these formulas. What's the stride value? What is the padding? And what is what kind of kernel you choose for? It depends on all like this. This is LeNet. And this one is AlexNet in 2012. The advantage with AlexNet is you can use 2 GPUs parallelly to train any algorithm. So in deep learning, most important things are how much time it takes to train the algorithm, and also what's the accuracy, whereas in case of testing. So this in AlexNet, you just say this AlexNet supports usage of 2 GPUs at a time. So like this parallel, but there are some interdependency here like this. With this interdependency, both the GPUs can train parallelly, so that training time can be reduced. That's possible with a group convolution, and so far achieved a 85% of accuracy through AlexNet. Then we move on to what's the group convolution is. Actually, convolution means like this. It's a series process, whereas in group convolution, it's a parallel process like this. We partition the given data into some kinds like this, like that, so that convolution is performed parallelly to reduce the training time. And next one is VGG 16, and also has VGG 19. The 1619 indicates that number of layers are 16, excluding the pooling layers, and the so far achieved recognized accuracy is 93%, and it was developed in 2014. And another one is it was invented by Google people. So they took the advantage of 1-by-1 convolutions here. 1-by-1 convolution. They first introduced 1-by-1 convolutions, and same way another one is previous all nets has a convolution followed by max pooling, but here max pooling is first and then convolution, so that they achieved a accuracy of more than 96%. And this is a ResNet. It's based on the feed forward path here. Feed forward path, and after convolutions and railing layer, so we can have a f of x plus x, and those will be given to the ReLU. So it achieved a 96 to 96.4%, and number of parameters to tune or train is 65 million parameters. So if someone want to develop a new net, they have to look for this how many parameters they have to tune, and what's the accuracy, and so on. And in case of DenseNet, it's a DenseNet means it's like a group of things, and there is some interconnectivity. If you see here, some interconnectivity is there, then that is called as a dense block. So parallel training is possible here through group convolution, which is introduced in AlexNet. And this is a mobile FaceNet, where they introduced a depth-wise convolution and point-wise convolution here. These all are to reduce the training time, where in depth convolution, what they do is n by n convolutions are performed parallelly here, and thereafter they are rearranged like this. Then we do the one-by-one convolution as like GoogleNet. How GoogleNet used this one-by-one convolution, that's we call as a point-wise convolution here. That's the advantage with the mobile face net in order to reduce the training time. And this is a shuffle net. Here you can see they used a one-by-one group convolutions and channel shuffler and some DW convolutions like this, and group convolution followed by it is a shuffle net, and there is a feed forward network is also there with this feed forward network is also there. That's the shuffle net. And finally, FNet is based on the concept of partitioning a 3x3 matrix into a 3x1 or 1x3 matrix like vectors. These are the vectors, and this is a matrix. So you can train K1 separately and K2 separately, and a multiple version of those two. It comes to the original one that is called as a FNet. And I have some results to show you, but I'm not including here. But as compared to PCA, I noticed that with these deep learning algorithms, results are better as compared to PCA. Then I moved on to the very important topic, that is fully homomorphic encryption. Here the cryptography actually started in those days where kingdom exists. They also do some encryption just by adding +3 like this. They send you one letter to the people who are far from the kingdom by doing some addition like C. Here A is replaced with D, T is replaced with W like that. And same way, as they know, this guy sent with +3, so they subtracted with -3. As simple as that. And this encryption is of two kinds: symmetric and unsymmetric. In symmetric, both encryption and decryption is done with the same key, whereas asymmetric. So these are some examples of symmetric encryption. So I think all of you know the Chiranjeevi name. After the evolution of this informatic theory, Chiranjeevi theorem. So the Chiranjeevi entropy, everything is shifted to next level. And these are the I previously told about RSA algorithm, and these are the guys. Their names RSA. These are the guys. In 1978. So RSA comes under as a asymmetric encryption. There one private key is there and then one public key is there. And asymmetric encryption is partially homomorphic encryption. I will look on to that also. And if you observe here, these points are the shows that these are encrypted with some encryption algorithms. And already I discussed about RSA. So as I told you, instead of placing X directly, let's apply some encryption so that no one can't see what exactly the X is. Suppose this is encryption of M1, encryption of M2. Suppose then its multiplicative homomorphism in the sense encryption after multiplication, encryption before multiplication here, like that. If these two are same, that is called as a multiplicative homomorphism. And similarly, additive also. So why XR and only used for this encryption data is with this anyone can any combination, any function can be realized with these XR and AND operations. So here is one example. suppose I0 and I1, and those are passed through some various XOR and AND operations to get some dB value of values 0, 1, 1, 0, like this. Suppose some example only this. And so far only for partially homomorphic is only possible, but fully homomorphic is also possible with some more concentration. In fully homomorphic encryption, everything is done on encrypted data only. Addition, subtraction, multiplication, whatnot. So far, all arithmetic and logical operations also can be performed with a fully homomorphic encryption. So this is the board invented this fully homomorphic encryption is possible. His name is Genti in 2009. 2009 it was, and he is a Google research scholar. Google research scholar who invented this. So actually, this idea came with the polynomials like here. So addition of these two gives this, and multiplication of these two gives this. And same way in matrices also, addition of these gives this, and addition multiplication of these two gives this. In same way, how about the integers? These three guys, these four guys, given here some detailed description about integer, how an integer is encrypted with encrypted, so that it supports a fully homomorphism. Suppose here to encrypt a bit B, suppose pick a random large multiple of P, say P into Q, like it's like a secure as a RS algorithm, and pick a random small number 2 into R plus B. So as we move on to the addition, subtraction, or multiplications here, then there may be a chance of improvement in noise here. So there is a hurdle here, implement in noise. So we need to reduce that noise. So here, suppose C1 is one encrypted email, encrypted data, and C2 is another one. If you add those two, so if you look at this, after addition is that, and after multiplication, if you look at this, this is the additional term which comes after multiplication. So we can treat this as a noise. This noise should be reduced, so that we can get back the original one. Otherwise, there may not be chance of getting original one. So the noise is growing as the number of multiplications.
Dr. Chiru, your voice is muted. Can you unmute? Your voice is muted. Can you unmute? Chiru, your voice is muted. Can you unmute?
Hello.
Yeah, unmute yourself. We are not able to hear you. Unmute.
Now it's okay?
Yes.
So here the problem is as number of multiplications additions are for more and more. That means addition of a encrypted data once again addition with another encrypted data. There may be a chance of incrementing in noise. That's why that will be possible. That noise will be removed with a bootstrapping procedure. So here, suppose noise is improved, then what we do is just we drop, we dig a valve here so that noise is getting reduced. So this process is repeated and repeated. Then finally, these are the improvements of what's the time required to do the encryption. It comes down like this here. It's more or less 10 below. It's almost all 80 seconds only. 80 seconds. Okay. Then how we use this fully homomorphic encryption in case of deep learning algorithms, that is called as a crypto nets. So as of now, in fully homomorphic encryption, addition, subtraction, and multiplication is only possible as many times as. So here, input is multiplied with weights. So multiplication is there. So it's possible. And similarly, after here, all those are summed. Means addition is there. So addition is also okay with fully homomorphic encryption. But whereas in activation function is a non-linear function. That may be a sigmoid function or something else. So there is a, but this function is not supported by this fully homomorphic encryption. That's why researchers replaced this with a simply f of x is equal to x square. So x square means x into x. So multiplication is possible there. So with that, we replace this activation function with a simple x square in case of fully homomorphic encryption. So still some research is going on about this activation function approximation, and some people did with filter designing, FIR filter and IEEE filter designing. There we can approximate the shape of this activation function as like a sigmoid function by doing some increasing the order of the filter. I like that. In similarly, crypto nets also replaced it. Where here we are multiplying, multiplication is possible and addition is also possible. But whereas in case of max pooling and average pooling, we don't have this operation is not possible with the fully homomorphic encryption. If anybody are interested to work on this, I suggest work on issues in conversion of ordinary convolution network to crypto nets, which supports a fully homomorphism. And these are some references. And finally, thanks to all for your patience listening to me for around 1 hour. Thank you. Any questions?
Yeah, thank you, Dr. Chiru, for your excellent overview presentation on robotics and also cloud fundamentals, followed by machine learning and deep learning and some of the security related items. There are a few questions. Would you like to take them one by one, right?
Yes, sir.
Can you briefly explain some protocols employed in machine to computer communication?
Mission to computer communication.
Some protocols.
I think that's not my.
Okay.
Actually, in literature only, I just gone through those.
Okay. And can you apply the cubic cubes principle for video editing and other thing?
Yes, sir. Only thing is, in 2D image is 2D, whereas video is 3D.
Okay.
So you can do it, but thing is, encryption time is more with the video. It's more almost like 24 times of image. Suppose if you do it with the image, if it takes 1 second means, in case of video, it takes 24 seconds, like that.
Okay. Can you briefly explain some of the cloud robotics platforms by web service providers like Amazon, Google, Microsoft? Because each
Yes.
one must be providing some platform, right, for
Yes.
using their web services
Yes.
to develop on the robotics applications. And just can
Yes.
you touch about these features, platforms?
Actually, I shown you that image and Amazon web services, no, AWS.
Yeah.
So actually, it's like very simple, sir. Cloud means they are maintaining a very huge equipment. It's like around 5 acres or 10 acres, like that. Google also providing it. So in AWS services, suppose let's take a AWS services as an example, where you have to create an account, and based on your from which you are come, like if you are a student, they offer you some kinds.
That's okay. No, we're just wanting that platform. What platform they use? Can you just sort of, what is the facility of AWS for cloud robotic development?
Yes, sir. Suppose in deep learning algorithms, some specific algorithms only run with the GPU only of 30 GB or 80 GB, like that, suppose. But if you want to buy it, it's very costly. But you can go with the Amazon people; they will provide you that.
No, there is something like called Robo Maker or something, that Amazon Web Services
Yes.
offer that.
Yes,
Yeah,
yes,
can you
they are
some features
offering
of
that.
Robo Maker? Yeah.
Yes, sir, they are offering those things also. Just
Okay.
what I did is I logged into it and I purchased one cloud server to my applications, which supports GPU and CPU requirements.
Can you provide some highlights on the research opportunities in this area?
Actually, the main objective of this cloud robotic is instead of using your own personal computer, you can go for cloud technology to increase the speed and onboard circuit limitations and so on. And in same way, I think just now I started with the cloud robotics, but mostly many people are using this. And these days, due to this coronavirus, everybody is working at home, so there may be a chance of more utilization of this cloud technology year after. I hope so.
But when you use the cloud, the latency is one of the major problem, right?
Mm.
So some of the cloud robotics applications are real time,
Yes.
like autonomous cars and health related
Yes.
medicine and surgery and things like that. What are the issues? If you have that latency when you use the cloud.
Yes.
how it can be overcome. We can overcome the
Sir, actually, why we moved on to the cloud means to resolve the problems exist so far with the personal computer or personal servers. Personal servers. Yeah, personal server is its speed is limited. So many limitations are there, and those all are overcome with cloud technology by adopting cloud technology. But only thing drawback with this cloud technology is you have to pay for them for their services, and same way how much time you are using the cloud is so one important for here.
No, that's okay. That we are only talking about the problems, associated problems, like the latency. How we can address the latency problem when you use the cloud facility.
Especially in cloud, only cloud. That means you want to. You're asking about what's the drawback with using cloud technology?
Yeah, cloud, particularly for robotics applications, like autonomous cars and things like that. What you had explained, no? There are issues like latency, security.
Yes, security. Yes,
So
mostly security is the issue.
yeah, yeah.
Mostly security is the issue. That's why we moved on to the fully FHE, fully homomorphic encryption.
Okay.
Yes.
And how can you use machine learning for labeling the images?
Labeling the images means is I think you know about object detection, and semantic segmentation. So where the algorithm is trained to recognize first algorithm is trained to classify the whether in the algorithm object is there or not, like object or a background, whether it is an object or a background, and once it is known, then there is a softmax layer at the end of the this at the end of this deep learning algorithms. It gives you how similar that object, or how much score that object is comes under object or a background. So in same way, so you can assign some labels. You have to assign. It's not like training. You have to assign those labels manually by giving some like 1, 2, 3 like that, or you can say dog, give us the dog, or like that.
And are there any research openings in your laboratory for this application? If you are
Yes, so many openings are with my lab. Not only with my lab, with some other professors also, they are looking for.
can you just explain how one can go about, because quite a few researchers are interested. So
Yes.
can you provide some guidelines how to go about applying and what are the requirements and funding opportunities?
Yes. Actually, let's start with master students. I don't know much about bachelor students, but for a master students, PhD and postdoc, there are several openings are ongoing openings are also there. Especially in my lab, also some ongoing opportunities also there. So there they call for the openings, and you have to apply. And if it's if it's your area and your interested area, and what the project is seeking, then obviously you will be selected for that. And here the cost of living is not so high, and half of that scholarship is enough for for your expenses, and rest amount you can save for your further future. And same way here in master level, PhD level, they are with by doing masters or PhD, or without doing that also you can have some opportunities, like you have to work under some projects, and whatever the targets of the projects you have to achieve. And every weekends there are some meetings, ongoing meetings are there, and so on.
Okay, thank you, Dr. Chiru, for your excellent presentation. Now I would like to request Dr. Saktivel to formally propose a vote of thanks. Dr.
Good evening,
Saktivel?
sir. Good evening to all of you. On
Sir,
behalf of the
Yeah.
ACM
I think
Chennai chapter.
Natarajan has a query. Natarajan.
Okay. Yeah.
Please, Natarajan, please go ahead.
Hello.
Natarajan.
Natarajan is muted, sir.
I think he raised the. I think you want to ask me something.
I think it's not there. Okay. On behalf of ACM Chennai chapter, Computer Society of India Chennai chapter, and IEEE Computer Society Madras chapter, we would like to thank today's resource person, Mr. K. Chiranjeevi, for his excellent lecture on deep learning algorithms for cloud robots. So deep learning, cloud computing, robotics, all are emerging areas, and he has presented a very nice introduction and overview about all these things. So on behalf of all the three societies, we would like to thank Dr. Chiranjeevi. Thank you, sir. And I would like to thank Mr. H.R. Mohan, Chairman, CSI Chennai chapter, H.R. Mohan, ACM Chennai chapter, and Mr. P.V. Subramaniam, Chairman, CSI Chennai chapter, and Dr. Akila, Managing Committee Member, Computer Society of India Chennai chapter, for their dedicated support in organizing this webinar. And I would also like to thank all the participants who have participated through this virtual mode actively during the seminar. So thank you, Ananda. Thank you very much. Thank you, sir.
Thank you, Dr. Saktivel. Before we formally close our today's meeting, I want to give some details about our forthcoming webinars. On 28th, we are having a program on COVID-19, the use of medicinal plants and environmental hygiene. This is going to be on 28th Saturday. On 1st December 2020, we have a program on placement scenario in the new normal. Basically, the placement scene has changed after the COVID-19. How one can prepare for the new placement scenario. That webinar will be handled by the placement director, Dr. Samir from Calicut NIT. So we are already sent invitations to all our members and others. So please register and attend these programs. Thank you. Once again, thank you, Dr. Chiru, for your presentation on behalf of the ACM, CSI, and IEEE. So we look forward to your relationship with us in the future programs. Thank you very much. And I also take this opportunity to thank all the participants for their participation and raising certain queries. Thank you very much, and we look forward to your participation in our future programs. Thank you.
Thank you all. Bye-bye.
Thank you.